So the first law that we're going to review is Charles's law. So this law specifically talks about temperature and volume. So we're assuming that we're not changing anything with the pressure. We're only looking at temperature and volume. And these have a direct relationship, meaning that they move in the same direction. So if the temperature increases, volume will also increase. So that's what we see here in this image. We see that it's getting hotter, which means that the particles are moving around faster. They have more energy and they're wanting to spread out. And so that's why it's taking up more space. Because remember, volume is really just the amount of space that something takes up. Because it's a direct relationship, it also works the opposite way, right? So temperature, if the temperature was to go down, like in the first image, that means those particles are moving slower. That means that they are now getting a little bit closer together. They're not spreading out as much. So the space that they're taking up, or the volume, is also going to decrease. This is why if you leave a basketball or your bicycle outside, maybe it's a very cool night, when the temperature goes down, it's going to look like that bike tire or the basketball has deflated, but really it's just because the gas inside, the air inside the ball or the tire, those particles have slowed down. They've come a little bit closer together, so they're not taking up as much space inside the ball. So it looks like the ball is deflated a little bit. The next law is Gay-Lussac's law. Again, this is a direct relationship, but we are talking about temperature and pressure. So we're assuming that the volume is going to stay the same. So that's why both of these containers in the picture look the same size, because we're not changing the amount of space that our particles are taking up. Our container is staying the same size. We're only measuring temperature and pressure. So again, this is a direct relationship. So what that means is if the temperature is going to increase, that means the pressure is also going to increase. So you can see in the second picture right here that these particles, because we've added heat to them, we've given them energy, they're moving around a lot faster, which means that they're just colliding into the container with more force. So every time these particles kind of bounce into the container, the edge of the container, that's creating pressure. Pressure is really just those particles pushing on the edges of the container. So every time, let's say this one keeps going, it's going to collide here. This one's going to collide, right? Every time they collide, that's generating that pressure. These particles are going to collide with the outside of the container a lot faster because they're moving faster than the particles in the first picture. Again, because this is a direct relationship, it works backwards. So if the temperature was to decrease, then the pressure would also decrease because those particles are not moving as fast, so they're not colliding with the container. One example is a spray can. You've probably heard you're not supposed to put those types of cans over heat, and it's because they can explode. Because the air or the gas inside that container is heated up, then all those particles are going to move even faster. They're going to collide with the container, and eventually the pressure inside the can will be so much that it causes the can to burst open. For Boyle's law, this one is a little bit different. We're looking at pressure and volume, and these have an inverse relationship. Basically what that means is opposite. So if the volume of the container decreases, like in the picture, then that means the pressure is going to increase. So you can see they're opposite. So if I forced all of these particles into a really small space, that means they don't have very much room to move around, right? They're constantly going to be colliding with the edges of the container because I've made my container so small. It would be just like if I put an entire class of students into the elevator. There's nowhere for you to go without bumping into the edges of the room, right? Compared to if you were just in the classroom, you could easily move around without bumping into the edges of the room. So in the first picture here, we have a large space. So we have a large volume, and you can see those particles are not colliding with the outside of the container very much, which means they have a low pressure. One example is popping a balloon. If you blow up a balloon and then you squeeze it, right? If you're pressing the balloon in, that means you're essentially decreasing the volume. You're making less space inside the balloon, which means that now all of those particles of air, they have less space to travel. So now they're going to be bouncing around, colliding with the edges of the container a lot faster, a lot more times, which is why eventually the balloon is going to pop. If you squeeze it hard enough, you try to make it small enough, it will eventually pop.